Hey, we decided to start updating you every week, every Friday, about the progress we have in Zolt project, in Zolt cryptocurrency we're working on right now. You most likely know about the project, but we feel that you need regular updates from me as an architect of what's going on and what technical issues and technical progress we have. I'm gonna summarize what we've done over the last 7 days, and you're gonna hear from me every Friday. So let's start from the first one. We managed to introduce master nodes. Those are the nodes which you connect to when you start working with the network. I mean your client. So you start a command line client, and then you tell your client to fetch the wallet from the network. When it happens, the client has to start talking to some nodes. If it doesn't know where to go, then it has to locate where are those nodes. And we had default ones. They were hard-coded in the repository, they were hard-coded in the source code, so the client knew specifically which IP addresses to use in order to start talking to the network. And we had 6 nodes. They are our computers, our servers. We pay for them, we maintain them, we make sure they always are online, and those are the default nodes. Now we decided to call them master and not just change the name, but we introduced one specific security measure against potential fraud and potential loss of trustworthiness in the network. When you fetch your wallet from the network, your client connects to a random number of random nodes, and some of them could be masters, which we completely trust. I mean, we mean the creators of Zolt network, of Zolt software. So when you fetch your wallet, the client will fail if the wallet is coming from only edge nodes, so-called. We call masters and edges. So masters are sort of a core of the network, and edges are all of the network, all the nodes in the network. So when you fetch the wallet and the content comes from only the edge nodes, that means that this operation is less trustable than comparing to the same operation which would actually fetch the data from at least one master node. So that's how we increase the trustability of the entire network. If somehow the software is corrupted, if somehow part of the network is run by people who we not trust, then still your client will tell you that the data is coming from the sources which are not fully trustable. I'm not sure we're gonna maintain this feature for forever. Maybe when the network grows, large enough, and we will have like 100 master nodes, maybe we will be able to transform it to something else. But at this point of time, when the network is still small, we are having like 20-30 nodes right now, which is quite small amount. We need this master status. And of course, you can disable that verification procedure. You can still fetch from the network, add the specific command line argument to your client, and then it will ignore this status. Master, edges, doesn't matter. The data is the data. So that was quite interesting improvement to our protocol. Garbage collection. Each node maintains a local database of wallets. Each wallet, as you know, is a file. It's a plain text file with all the transactions inside. So each node maintains a certain amount of those files. But some files may be empty. You can create a wallet, you can push that wallet to the network. All the nodes or many nodes will catch your file, will maintain it locally, will store it, and will keep it there. But then you make no transactions. You just pushed an empty file with the ID and a public RSA key inside. But there are no transactions. So those files they're not necessary. The network doesn't really need them because there's no data inside. They are not involved in the verification process, in the merging protocol. So we just don't need to keep them there. So we decided to introduce the garbage collection because we had like 27,000 wallets in our master nodes, And many of them, like 70% of them, they were empty wallets. So somebody created them, pushed to the network, and forgot about them. So this garbage collection, the garbage collection routine is what nodes are doing. They're just running through the list of wallets. They're going through all of them and deleting those which are empty and too old. Like nobody touched them for the last 10 days. We use 10 days right now. This garbage collection is not affecting the security of the network anyhow, because if those wallets are usable, if those wallets are needed, are still in use, then their authors, then their owners will still have their private RSA keys and will be able to restore the content of the wallet locally. But if their owners are not interested in those wallets anymore, they'll just forget them, and the network will forget them, and it's no harm done. So we introduced that garbage collection. Memory leakage. We still have, as you know, we still have the memory leakage problem in our nodes, meaning that the longer they run, the longer they stay online, I mean our Ruby software, the larger it becomes in memory. So the statistics show that, let me check right now, that some of the nodes are as large as 7 gigabytes, 5, 4, 7 gigabytes. If they stay online for like 7 days, if you run the node software for 7 days, it may grow in memory up to 7 gigabytes. That's way beyond any limits, because we don't need that much memory. We need like 100 megabytes, 200 megabytes, that's all, because we keep the data in files. We don't keep the data in memory. We only cache the data in memory sometimes. So that's obviously a problem in our software, obviously a defect, a technical issue which we're trying to fight with for the last month, or maybe a little bit more. And over the last week we made some progress. We made some progress in the way that we are not going outside, completely outside of memory. We're not hitting the out of memory exceptions anymore. So we are big in memory, but we're not unlimited. We're not running up to no limits. That's an achievement, I would say, but still, it's not a final solution. We need to find a way how to keep our nodes memory efficient. But that was an achievement for the last week. And financial model. We managed to invent an experimental model to control the price of Zolt coin in relation to some other more stable cryptocurrencies, and make sure it grows constantly, periodically, in a predictable way, using the finances which we take from Xerocracy business as donations to support the coin. More details will come later. I'm just announcing you that that's the financial model which we've been working for a few months. And just a few days ago, we managed to come up with a schema of how it will work. I put it on a Telegram group, and you can check it out there. It's still in development, but I think we're onto something. I think that model will actually help us a lot to to motivate people to gain those coins, to hold them for some time, to get some profit from it, and not in a speculative way. Not in a way just to gain profit from trading stuff, but actually to gain profit from helping Xerocracy business. As you know, Zolt cryptocurrency is all about being a vehicle to drive Xerocracy forward and help the world of software development and the world of project management to improve. That's what Zolt cryptocurrency was created for. So it's not a speculative coin. It's not a coin, to help us all make money out of nothing. We will make sure that Zolt grows when Xerocracy business grows, and Xerocracy business grows when Zolt grows. So they will help each other, at the same time helping programmers, live better lives and software projects be more successful. So that's what we managed to do. And now about the problems. We still have problems, technical things for the future. First of all, memory leakage, like I said. We need your help. If you can help us out, if you can, look at our Ruby code and investigate what's going on there. I'm working on that now, but I need second hands. But I need your help. So if you can help, join in. It's an open source project written in Ruby. Sinatra is the is the web framework. Memory is managed by our own stuff, so it's not so complicated, but still memory is leaking. Queue overflow. We sometimes experience situations where nodes are getting too many incoming wallets, and there is a queue there, like a buffer, which accumulates those wallets before they get into processing. And sometimes those queues grow to large sizes, and nodes stop responding to new push requests. It's not happening quite often, it's maybe sometimes, but still we experience those situations time to time, and we need to work on that to find out where we most likely duplicate data. So we're not having obviously that many wallets right now. We're not having that many push requests right now. Obviously we have some dead loops somewhere. So we're pushing to each other. So we're duplicating transactions, duplicating operations, duplicating push and fetch operations. That's why the queue is growing. And problem number 3, it's large traffic. I think this problem is connected to the problem number 2. So the queue is growing for some reason, and we have quite often a large amount of traffic from node to node. So they're not supposed to exchange, big chunks of data. They're supposed to stay quiet more or less, and only when something happens, when some new transactions show up, when some new wallets are updated, or new wallets are pushed, or old wallets are updated, only at that point of time, nodes are supposed to exchange the data through HTTP protocol. But it seems that now they are exchanging data too frequently, and the data which is redundant. So they exchange the data which they already have. And that's again a technical issue which we need to work on right now. So we need your help, we need Ruby development help, and we need to, Ruby experts. The project is not so technically simple, fortunately or unfortunately, but we need help. Thanks for listening. See you. You will see me next Friday. I'll keep you updating. We obviously have progress every week, so stay tuned. Thanks for listening, and thanks for being with us.